Pleasure to have Julien from the Laboratoire Univers et Particules in Montpellier. It's the lab of the University of Particles. In Montpellier, Julien has been there since 2011, and before that, he did postdocs all around the Mediterranean basin.
Around my wife, actually.
I'm sorry?
Around my wife.
Marseille, Berlin, and Madrid, and then his PhD at Montpellier, where he joined again as a CMS researcher. He worked on a variety of topics in dark matter phenomenology, such as indirect detection of dark matter. He also worked on high energy cosmic rays and neutrinos. Am I right? And so today we're going to hear about the dressing of primordial black holes with dark matter.
Okay, thank you for the kind invitation. So it's really a great pleasure for me to be here and to visit this institute. Really nice, really good. And yes, I'm actually visiting the MIT for month of April, which provided me with a time slot to visit here. Pretty good. Yeah, so today I'm going to discuss well, a mixed dark matter scenario in which you would have both primordial black holes and relics. And and it's based on a collaboration with previous postdocs and students, Mathieu Boudot, Thomas Lapoire, Martin Streff, my well, collaborator and friend Pierre Salati from ANSI, and recently Vivian Poulin from Montpellier and Pearl Sandy from the University of Utah have joined the project. So it's based on published work and also on in collaboration. All right, so yes, just to start, just to avoid any confusion. So about the Montpellier I come from. So Montpellier is not Montpellier, Vermont. It's Montpellier, south of France. So it's located on the seaside here. So it's one of the few cities in France where you have this kind of arc de triomphe here. And Montpellier is well known for its very old school of medicine, which is 800 years old. And it's also known, for instance, if you're interested in alchemy or this kind of, prophecies, etc. It is known also for hosting Nostradamus Tower, from which he observed the skies and planets, etc. So Montpellier is very attractive to students, as you see, because it's on the seaside and you can make friends with these beautiful flamingos. And regarding science, it's also known for for having hosted Edouard Roche, who is known for the Roche limit in the context of gravitational tides, for instance, and also Alexander Grothendieck, who is a very well-known mathematician, known for his work on algebraic geometry, and for more physics-related topics. My senior colleagues are, for instance, André Neveu from the Gross Neveu model, David Polarski, one of the CPL guy. CPL is quite discussed nowadays in the context of cosmological tension, cosmological dark energy, and Karsten Jedamzik, who is also known for his work on primordial units.
Can you
welcome.
avoid letting your voice drop sometimes if you're
sure, sorry. All right, so let me move to science now. So it's becoming more and more difficult to make a proper introduction on cosmology because of these tensions showing up everywhere. Well, I should say that for dark matter, maybe it's a bit less, less subject to tensions. And regarding dark matter, what is impressive, at least in the context of the standard model of cosmology, is that what is very much related to dark matter is structure formation. And structure formation is a very big success of the standard model of cosmology, and it relies on basically two things. The first thing is the properties of primordial perturbations, which can be related to some inflation scenario, for instance, which is a good model for that. And also to the properties of dark matter itself. Kinetic decoupling, things like that, self-interaction, things like that. And in the standard model, what is also very impressive is that even though structure formation is non-linear, the final output is a one-parameter model. So basically, if you give me the mass, I give you the properties of halos, and you know all about the mass distribution of halos in the universe and their properties. So this is only relying on dark matter. Of course, if you are probing small scales, well, the centers of galaxy, things get more complicated because of variance. But this is basically one of the big success of dark matter cosmology. Well, if I have to put things into context, I still have to talk about, well, tensions on small scales. So for the dark matter, well, component, the tensions come in subgalactic scales where you have this core and cusp problem. So the fact that in dark matter only galaxies, you would expect cusp, while you find cores in many observations. Well, and this is actually coming from the interpretation of one of the oldest serious hints for dark matter, which are galactic rotation curves. So you have the circular velocity as a function of radius. You have a bunch of data here. So the asymptotic value of the velocity tells you about the mass, and the inner velocity value tells you about the profile index at the center, right? And so basically you can recast these rotation curves in two different planes. One is this one. So you have the acceleration due to baryons as a the total acceleration as a function of the acceleration due to baryons. And you see that in this plot, you have a very small scatter. This is very strongly correlated, both of these accelerations. And this is reminiscent from the Tully-Fisher relation, so the matching between the velocity and the mass of the object. And on the other hand, you can recast these rotation curves in another plane, which is circular velocity at the center, which somewhat measure the inner slope of the profile as a function of the maximal velocity, which is a proxy for the total mass. And you see that you have a strong scatter in this plane. So you know that this kind of core and cusp discrepancy can be rephrased in terms of diversity versus regularity problem. So this is kind of well, a new formulation of tensions on small scales. So of course, when you are dealing with small scales, well, there are baryons, so it could be simply the effects of baryons, which are at stake here. But this also motivates solution in the dark sector. And for instance, this has been a strong motivation for self-interactions and ultraviolet dark matter. Well, so in my talk, I will actually, well, not follow this line, and I will assume that there's no tension in the dark matter sector. And the assumptions I will make is that dark matter is not strongly self-interacting, it's not ultralight, and it's, well, merely cold and mostly collisionless. And not only it's made of one cold dark matter candidate, but it's, well, there's an additional dark matter candidate. So that would be both thermal relics and primordial black holes. And so this is kind of a composite scenario which has been already studied in several times in the rest. So basically, one of the important free parameters is, of course, the fraction of black holes in the universe, which can help you with rescaling over quantities. All right, so now as for the PBH landscape, so you are probably very familiar with those plots. On the left panel, you have the fraction of dark matter in the form of black holes as a function of their mass here. And so you have a bunch of constraints showing up. And well, basically all the available mass range is populated with constraints, as you see. So it goes from, say, 10 to the minus 18 solar mass up to 10 to the 20. So it's a huge range in mass. And basically, there's still this spot surviving constraint, which is called the asteroid mass window. And basically, in this mass range, black holes would make up, well, say, 100% of the dark matter. Well, this has to be combined, of course, with this kind of plot on the right panel, which is the amplitude of the primordial power spectrum as a function of the wave number. And well, the realm of, primordial black hole dark matter would be these very small scales, where you would expect primordial black hole to contribute a significant fraction of dark matter.
To resolve the axis.
Yes. So,
can you just...
so it's 10 to the 4 here, 10 to the 8, 10 to the 12. So it's an inverse megaparsec scale. Okay, so it's very small scale here. And so the CMB constraint are shown here. And here in this blue region is where you have constraints from galaxy surveys, for instance, or Lyman alpha. And well, and this is the prediction for vanilla inflation, scale invariant inflation. Well, you would have the amplitude of a power spectrum, which is scale invariant. And well, in order to get a large fraction of black holes as dark matter, you need, of course, to increase by a lot the amplitude of the power spectrum. So this is assuming that perturbations are Gaussian. But well, you could also invoke some strong non-Gaussianity on small scales in order to have also black holes.
Sorry, so how am I supposed to read the plot on the right? The colored regions are.
Yeah, so this is excluded. So CMB provides you a very stringent constraints around here. So the amplitude has to be really confined along this line. Okay, so this is very much consistent with the predictions from inflation, for instance, the kind of scaling variant spectrum for perturbations. And if you extend this kind of vanilla prediction, this is what you get. So this would be kind of a natural expectation value for the amplitude of the power spectrum, and this is actually what you need. So you need to lie here in order to have black holes. Being 100%.
Is the place you want. I'm confused about the red and the blue and the.
Yes, exactly. So you want to saturate here in order to get black holes being 100% of dark matter, basically. So you need a huge amplification of the amplitude with respect to this vanilla line in order to get black holes are the main component of dark matter.
So what's the difference between the red and the blue lines?
So well, these are constraints from so what is it now? Let me try to remember. This is coming from this paper. Yes, so these are expected constraints from PTA, and these are expected constraints. I don't remember. Maybe it's.
I think PTA is just the dashed line, but if you go to the right of your plot, I think it's calculating.
Well, I don't really remember, but 10 to the minus 2 is typically what you. Between 10 to the minus 2 and 10 to the minus 3 is typically the amplitude you need to have 100% of dark matter. Right. So if you saturate that, you get the full.
If I remember correctly, the paper, in one case they have a monochromatic delta-like spike in the power spectrum. In the other, they have sort of normal.
Yeah.
Or they also consider non-Gaussianities. So maybe in one case they have non-Gaussianities, and in the other they have a sort of.
Yeah. So it's probably related to saturating the fraction given those.
But yeah, the lines are drawn in such a way that you saturate. You get that deviation.
But actually, that provides you with a huge difference in scales.
So let me see if I'm not sure I've still grasped it. But it's the idea that if you were consistent with the left plot,
yes,
you could allow structure in those red regions on the right plot, that would be okay.
Yes. This is not excluded. So you could.
So the green part is excluded, but the red.
Yes, exactly. So you could cook up a model that would provide you with some extra power on some scale, and this is not excluded yet.
And where's the PTA signal if you interpret it
What's
as?
excluded is what's it called?
This one? The PTA signal.
Yeah.
I mean,
The colored regions are excluded.
Oh, okay.
Like the power spectrum.
so I don't know exactly.
What's the primordial power spectrum?
Right, because
All right, maybe I can.
it's big at the top. I can't read any of the things. Okay, thank you. I can get that.
All right. So anyway, it might be a bit difficult, I mean, to have naturally 100% of dark matter in the form of black hole, but still, I mean, this still motivates an interesting question, which is what would be the consequences of a quantities if you have even a subfraction of black holes in the universe? That's what I'm gonna try to discuss in the rest of it. All right. So this composite scenario in which you have black holes and thermal relic is not a new idea. It has been already studied in the past, and it was studied essentially in the context of some kind of accretion model, which was studied by this group of people, Mark Ostreicher and Ricotti, in the 2000s, in the 20s. This was also studied by the Russian school and around Berezinski, for instance. And well, the idea was in this context to grow, to study the growth of dark matter halos around primordial black holes. And the idea was to enhance the accretion efficiency of baryons. That was the idea. So if you have an extended halo, you have a more massive system, so you are more efficient in dragging baryons from gravitational effects. So that would enhance the accretion rate of baryons, and then you could, probably think about sources of intermediate mass black holes due to this enhanced accretion of baryons. And you can think about also a potential explanation for ultraluminous X-ray sources, which have been observed already quite a few times. And so this model is based on a fluid description of dark matter, and it was leading to some kind of power law behavior of the dark matter halo building up around these black holes with some slope, this kind of scale invariant solution in this context. And this kind of accretion model was used later on by Lavalle and Beacom in the early 2010s. And well, the idea was to assume that the other dark matter component would be made of WIMPs. And in that case, since you have a spike of dark matter around the black hole, you would trigger some annihilation, and you could then probe the population of black holes based on the annihilation products. So you see that if you translate this kind of scenario in terms of the abundance of black holes as a function of the WIMP mass here, you get this kind of constraints, which are telling you that, well, actually, if WIMPs do exist, then you can basically probe fractions of black holes which are very, very, very tiny. So you have to remember this kind of number is 10 to the minus 6, 10 to the minus 7 in terms of fraction. Okay, but this model was based on this very simplified fluid accretion description. This was based also on assuming a slope, a certain slope for the profile, and I want to go beyond.
Question, was the idea that at later times you make an NFW halo? This is like a seed or something?
Yes, this is like a seed. So the external region will indeed behave like a secondary info. So you would give rise to classical halo, but the very central part would be a bit different. All right. So in fact, the big step forward was made by Eroshenko in this very beautiful paper, dark matter density spikes around black holes. And he came with this brilliant idea, which is just that, in fact, if you have thermal relics, you know exactly the initial condition at the time of kinetic decoupling. So the time when particle stop to interact with the relativity plasma. So it's a Boltzmann gas, you perfectly know the initial condition. So since you know the initial condition, you can actually fully integrate the orbits. This is a two-body problem, okay? The dynamics is completely dominated by the black hole. You can integrate the orbits numerically, and by construction, you get all the effects of the angular momentum, for instance, which is very difficult to include in a fluid description. Okay, so this was a very brilliant idea, and you see that the results are very spectacular. So this is the log density of the dark matter spike around the black hole as a function of radius. So these are different, assuming different masses for the black hole. So the seed black hole. So well, you don't see any line continuing here, just the Schwarzschild radius corresponding to more and more massive black holes. So there's nothing inside. Okay, but you see that there's some kind of scale invariance. You have power laws basically here. So there's some kind of scale invariance showing up in this problem. And actually, this kind of calculation was used later on in order to redo the analysis of Lavalle and Beacom on constraints. And so, in fact, when we've seen that, this scaling relation, we were interested in trying to understand really from analytical basis the origin of this scaling invariance. Okay, so the idea was really to revisit this work.
Could I
And-
just,
yeah.
for orientation, would the sort of picture in the back of people's minds be that every halo approximately would have been seeded by a primordial black hole? Or is it indeterminate or?
No, in this
Nobody-
context, it's not necessarily the case. So every black hole in this context would see the spike around it, that's for sure. But you would have also halos forming from, well, a standard structure formation. So big halos would be populated with black holes, for instance, but they would also follow the same structure formation history as the standard. So around each individual black hole, you would have spikes, but these black holes would contribute well, classical galaxy formation as simply test particles.
But what should I think in terms of sort of the fraction of the total dark matter mass that are in these prime and the seed black holes?
The total fraction of, well, it's a very small component, and I will explain this to you just now. So this is just a sketch in order to explain you the mechanism, and then you will understand what the fraction is from that. So on top, I just show the timeline, and so this restarts early in the radiation domination. So I just assume that we are after thermal freeze out, so chemical decoupling has occurred already, so the dark matter abundance is already set. Okay, and I'm considering a black hole sitting in the plasma here. So even though chemical decoupling has occurred, there's still kinetic interactions between the plasma and dark matter particles. So they are colliding with each other. Their scattering still ongoing. Okay, so the dark matter at that time still feels relativistic pressure. Okay, so it's dried away from the black hole, and basically it cannot fill the black hole itself because of relativistic pressure. Okay, so they're scattering, but from this time, I can already think about some kind of gravitational influence region around the black hole. And a very, well, say, simple way to think about this gravitational influence region is to define it by assuming that the radius of this zone is the radius below which the mass the mass contained is less than the mass of the black hole. Okay, so you can think about this zone like that. So of course you can relate the total density to time, and you can revert this relation and get an expression for the influence radius, okay, as a function of time. Okay, so I just write down the influence radius, which scales like 1/ρ to the 1/3. And I just put the time dependence of rho tot, and I get this. And if I rephrase that in terms of scale factor, I get a to the 4/3. Okay. So now the question I can ask is, what's the dark matter density at this particular radius? Okay, which of course increases with time. So if I trying to figure out the dark matter density, so the dark matter density scales like the inverse volume, and so if you change the scale factor, if you trade the scale factor with the influence radius, this is the scaling law that you get. So it's minus 9/4. So it's really the classical radial info solution that you get here. Okay. So, but this is assuming that I'm just considering the decreasing of the dark matter density as time goes. So you would assume that the universe is just frozen, and you just pile up some kind of onion shell around the black hole. Okay.
Quick question. Stop me
Yeah.
is next, but
Yeah.
would you get like annihilation spikes where you have the caustics from secondary info?
Yes, I will discuss
Oh,
that
okay.
later on.
Thank you.
Yeah. All right. So in fact, you can actually rephrase that in terms of more sophisticated arguments. You can write down the equation of motion in an expanding universe with a local curvature. which would be some kind of mimicking the presence of the black hole in an expanding universe. And what you get actually, well, you have to solve this simple equation. And actually, you can already see that you have some scale invariance here. And this scale invariance provides you with a relation between the turnaround radius and the time of turnaround. Okay, and this is somewhat also related to Kepler laws, basically, because you have exactly the same state. So basically, you can rephrase the turnaround radius in terms of this more sophisticated expression, but this is exactly the same scaling in time. Okay, right. So now there's a very important moment in the story, which is this one. So the time of kinetic decoupling. The time of kinetic decoupling is very important because it's a time from which dark matter particles can freely fall onto the black hole. Okay, so they don't feel relativistic pressure anymore. They are free to fall onto the black hole. Okay, so what's important is that at this time, so you have a specific kinetic decoupling radius. So I will call it, so it's the influence radius at the time of kinetic decoupling.
Can I have to go back a slide, I think.
Yeah.
Your influence radius seemed to be independent of the dark matter density, but I think
it's the total density that matters. It's the total mass inside the volume. So dark matter is included in. So it's radiation plus dark matter.
I thought, oh, I see, rho total.
Yeah.
Okay, good. In that.
Yeah, it's rho tot here. So it's a radiation plus dark matter. Dark matter is there. But then that probably answers your previous question, because the dark matter fraction at this time is very small.
Mm-hmm.
So you can imagine that the fraction
primordial black hole fraction.
Assume that you have a small fraction of black hole, so it's irrelevant to the abundance of dark matter. But even though the dark matter component very early in the radiation domination is small, it's a small component of rho tot, right?
Rho total is the total density.
Yes,
of everything.
radiation plus
and,
dark
sorry, you
matter.
said that, but I just didn't.
Yeah.
Okay, I see. Okay.
All right, so this time is very important because, well, kinetic decoupling is the moment from which dark matter particle can fill the black hole and start orbiting around the black hole. So what is important here is at the time of kinetic decoupling, the density in this region is homogeneous, right? Because you have an homogeneous universe here to start with. So at the initial time, before free fall, at the initial time, precisely at kinetic decoupling time, the density here is constant. Okay, is the density at the time of kinetic decoupling. And so you can also about the initial condition in phase space, because it's a Boltzmann gas, so you know exactly the velocity dispersion at that time. Okay, okay, so you know everything about the initial condition within this sphere. Okay. So this is this kinetic decoupling radius. I will use that in the following. So keep that in mind. So inside the kinetic decoupling radius, the density is constant at the kinetic decoupling time. Okay. So then, of course, as time goes, the shell, well, the influence radius increases, and so you pile up more and more dark matter around. But of course, as time goes, the density of dark matter decreases, and the dispersion velocity also decreases. So at each onion shell, basically, you have different dark matter density and different dispersion velocity, just because of expansion, All right, so from this, you can imagine there's a piling up of shells that gives rise to a spike of dark matter around the black hole. And this spike, the fact that it's very compact and very dense, comes precisely because the time of formation is very early in the universe. So it's really critical. The important point is that they do form in the radiation domination. And then, of course, if you have self-annihilating dark matter, well, you come up with a new high energy source that you can try to trace in this sort of the universe. All right, so let me try to go into slightly more detail. Well, this is what happens once a particle starts orbiting the black hole. So you can write down the condition for this. It's very simple. It's classical mechanics. So it's condition on energy and conservation of energy and angular momentum along the orbit. And of course, a particle which is injected at any point can probe radii between the pericenter and the apocenter. So this particle can contribute density everywhere between the pericenter and the apocenter. So if you want to determine the density profile around the black hole, and you see it here, you want to determine the density at this position, you need to pile up all the orbits that contribute some mass element at on this shell. Okay, so you can write down this very simple equation. So the contribution in this shell around the R is given by the sum of all mass elements that cross this shell. Okay, and this mass element can be written in very simple terms, in terms of the initial condition that you can trace along the time. Okay, so this is the initial density that corresponds to a given initial radius, and this is the Maxwell-Boltzmann velocity distribution here. Okay, so everything is known from the beginning. You know exactly the initial condition. And of course, inside the kinetic decoupling radius, everything is constant. But once you start integrating radii which are above the kinetic decoupling radius, you start probing regions with less and less initial densities and less dispersion velocity. All right, and well, something important is one of the very few examples in structure formation where you have the formation of a halo which is fully linear. And it's fully linear just because it's dominated by the black hole. The dynamics is completely dominated by the black hole. That's the only mass, the only important mass is the mass of the black hole in this story. And just because the dark matter density is subdominant at that time. You remember, rotot is, the dark matter density is a subdominant fraction of rotot. All right, so if I sum up, I can write down the density profile around the black hole. So this is just this phase space integral. And well, there's some kind of subtlety. So below, you see, in fact, the probability of having my dark matter at position R given the initial condition given by position and velocity. Okay, so this is the inverse of the orbital period here. And here, below the square root is simply the radial velocity, okay? Square of radial velocity. And it turns out that in Eroshenko's paper, there was a small mistake, in fact. So you see that this big Ym was dubbed a squared, okay, in the original paper of Eroshenko. And in fact, dubbing this a square means that it cannot take negative values unless you assume some kind of weird description with the imaginary numbers. But well, if you inspect carefully this radial velocity, which depends on y, you see, for instance, that if you inject some particle at the apocenter, assume I inject a particle at the apocenter, so by definition, the cosine at apocenter is 0, okay? So that means that in order for the radial velocity to make any sense along the trajectory, Ym must be able to take negative values. So obviously cannot be a square, okay? And that was a mistake actually which propagated in the literature over all the papers using this kind of thing. Well, and of course, Ym can take negative values. So this was a mistake. And in fact, this Ym values also affect the lower boundary of this integral. So you see it's related to the Ym here. So there was kind of mistakes which propagated in the literature. So we show you what it means. Well, now in order to get both analytical solutions to this equation and in order to understand the importance of taking Ym also negative, I can recast the canonical phase space volume, which is position versus momentum, in terms of new variables which are shown here. So on the y-axis, you have the ratio between initial kinetic energy per unit potential energy. All right. So that means that everything that sits above 1 escapes the system. So it's not bound to the system. Okay? And on the x-axis, I just put the ratio between initial position and destination position. Okay? So you see that at 0 velocity, the injection point is by definition the apocenter. So it's the farthest region you can probe afterwards. So basically, what is below 1 here cannot be reached by any trajectory. So it's excluded. This cannot be reached. It's beyond reach. Okay, so this is escaping, this is beyond reach. What you have to integrate over, what is bound to the black hole, is this gray region here. Okay, so now you see on top of this, I draw lines which correspond to null values of Ym. And you see that these dark gray regions are those regions where Y is negative. So you know that there's a significant part of the phase space with negative values for Y. Now, what I can draw is a constant initial velocity. I fix the initial velocity, okay, at different values. And if I fix an initial velocity, and if I want to integrate over space, over radius, this is the line over which I have to integrate the system. So radial integration means integrating along these straight lines crossing 0 here. Okay, so you see that when you perform the radial integral, you have regions where you cross this boundary. So this gives rise to numerical instabilities, which are not physical divergences. This is numerical divergences, but not physical ones. And this means that you have to be very cautious in doing the numerical calculation. So this is what you get when you do not. So this is the log density as function of log radius, as before. And the dashed lines are what you get when you do this mistake of not considering negative values for Ym. So this is what you get, the dashed line. And the solid lines are what you get when you do the calculation properly. So you see that, in fact, you can have orders of magnitude differences in the final results. All right, so let me now comment about this profile. So this is again a low log density as a function of log radius. And so I'm just picking values for the dark matter particle, the dark matter particle being 1 TeV here, and X is the ratio between mass and kinetic decoupling temperature. So it's 10 to the 4 here. And in color, you have different masses. So the red line here is the lightest object, which is 10 to the minus 18 solar mass for the black hole. And yes, the magenta line here is 10 to the 4 solar mass. Okay, and so I'm scaling up the mass of the black hole that way. So what you see is that you have different slopes showing up in this calculation. So you see that for light black holes, you have kind of two regimes. One is a slope of 3/4 and 3/2. In the intermediate regions, you have 3/4, 3/2, and 9/4. And in the massive region, you have 3/2 and 9/4. So 9/4 should remind you about you know, this radial solution, this radial info solution that I was discussing just before. And I will explain to you.
So where's the 9/4? Is it like the almost vertical part? Where is it supposed to?
Sorry,
Where's the 9/4 slope?
So the 9/4 slope is this one.
And so
this is the 3/2, and this is the 3/4.
So for the blue line, the 3/2 is at the very left.
Yes, exactly. Exactly.
Are you going to show how this depends on the kinetic decoupling temperature?
Sorry?
This X that you're fixing to 10 to the 4, are you going to vary it?
Yes, I'm going to vary it. And of course, everything depends on the initial parameter. So if I change X, I will change the results. So X is kind of measure of dispersion velocity at a given time. Okay, so of course, there's a hierarchy between potential energy and kinetic energy, and that plays a role. All right, so this is exactly the answer to your question. So different particle masses on top, on the vertical line. So 1 GeV, 1 TeV, and different XKD values on the left and right. So you see that if I just play with XKD, you have to compare left and right, so you see you have differences. Okay. But you see that, well, in fact, the point is that the scaling relations, of course, depend on the initial parameters. And so the questions we wanted to answer is whether we could make analytical sense of that. And the answer is, as you can guess, is yes. So I'm showing you exactly the same phase plot as I was showing before. So you have the ratio of kinetic energy to potential energy at the initial time, initial condition, on the y-axis, and on the x-axis is again the initial radius and the destination radius. And on top of that, I'm just showing, so the integration region is this region here, dashed. Okay, so it's where the dark matter is bound to the system. On top of that, what I can show is the phase, the extent, the spread of the phase space for a given scenario. Okay, so I'm picking up a value for the dark matter particle, and I'm picking up a value for this decoupling temperature. Okay, so then, okay, I can consider either a destination radius which is larger than the kinetic decoupling radius. Okay, so this is shown in yellow here, and I can take also a region which is inside the kinetic decoupling radius, which is the blue region. So in fact, you just stretch this value here. So now, if I'm picking, I will concentrate on the yellow-brown region to start. So what I'm doing here is that I'm considering the spread of the phase space, and this is described in terms of the spread of the velocity dispersion. So what I'm measuring in the vertical axis is the ratio between kinetic energy and potential energy. So what I can show you here is replacing the initial kinetic energy by the dispersion energy available. So the peak here, it corresponds to the kinetic decoupling radius. So you remember that inside the kinetic decoupling radius, to start with, the velocity dispersion is constant. Is everywhere the same inside the kinetic decoupling radius. Okay, so this has to scale linearly with the radius just because of this relation. Okay, so in this plot, I have simply a linear relation, and you see that my region can extend away from the escape down. So here I'm considering a model for which the velocity dispersion at kinetic decoupling time is above the escape velocity associated with the black hole. Okay, of course I can play with that. If I increase the mass of the black hole, I will simply compress this region downwards. So you see, if I increase the mass of the black hole, I will simply compress, and I will get here, and then I will get there. Okay, simply by changing the mass of the black hole. And I can do exactly the same. So this is at kinetic decoupling, and you see that between kinetic decoupling and equivalence, matter radiation equivalence, the dispersion velocity will decrease simply as a consequence of expansion. Okay, so the phase space will actually decay down to this point as time goes, and I can do exactly the same. I can play with the mass, such as this point corresponds to that mass. Okay, and these are so the yellow and the blue simply are using different destination radius. Well, now you can understand that from this very simple analysis, I can extract two different masses. So the first mass I can extract is by putting this down to the bound region. Okay. So if I arrange to get the velocity dispersion equal to the escape velocity, then all my phase space is included. Okay, in the bound region, and I can do exactly the same at equivalence. Okay. So this provides me with two black hole mass scales, two values for the mass of black holes given some dark matter, some dark matter ingredients. So now you can understand that when the mass of the black hole is lower than this mass, that means that you are in a region where the dispersion velocity dominates over the potential energy. Okay? And then you can play around, you can enter the intermediate region where you are in between. And you can get also into a mass region where the black hole is so massive that by definition, the dispersion velocity remains everywhere below the escape velocity. So it's a regime where the potential energy dominates over the kinetic energy strongly. And I was telling about three slopes, and basically you have three regimes here. And of course, the solutions are this. So instead of showing you some complicated equations, I can show you a phase diagram for the slopes. So on the y-axis, you have the mass of log of the mass of black hole as a function of log radius. And if you want to, describe a profile, you draw just an horizontal line in this plot. So if I'm picking a mass of the black hole and I want to know the profile, I just drawing an horizontal line. What I get is that I first cross this green region where I have the 3-4 slope. Then I cross the darker green region where I have the 3L, and then I enter the region where the potential energy dominates, the 9/4. Okay, and so at any mass I can draw horizontal lines and get the profile. So of course we get a very complete analytical understanding of these slopes, and basically the 3L is the one which corresponds to some kind of Kepler scale invariance. No? Kepler, well, 3F is reminiscence from Kepler rules, actually the relation between orbital periods and orbital radius. Okay, and the 9/4 is really reminiscence from this radial in-4 solution where the potential energy dominates over the kinetic energy, where you can consider that particles are frozen basically. And this region is much more complicated. It's actually some kind of, this is the region where you have some caustics. It was a complicated region. Anyway, so before, well, up to now, I've not considered annihilation. So this can be applied to any dark matter candidate, which is non-relativistic. Non-relativistic dark matter should, in fact, follow the same kind of behavior around black holes. So now I'm turning annihilations on. And so, of course, what you have to consider is that the annihilation processes will deplete the dark matter density in the central regions. So what you can solve is this kind of evolution equation here, which is telling you the evolution of dark matter number density, which is evolved due to annihilation. And this equation is actually still correct while the annihilation is S-wave, so meaning velocity independent, say. If it's velocity dependent, you have non-linear effects, of course, but if it's not velocity dependent, it's still linear. And it is valid in a radial case, radial in-fall case, okay? Or it is valid both in the radial in-fall case and in the case of circular orbit. So you can use this equation in these two cases.
What do you mean by so linear? What is linear in what?
Well, linear in the fact that, well, this evolution doesn't care about the phase space distribution at all points. Okay. Otherwise, you have annihilation that depends on the local density, but you have a flow which is not complete. Well, your particle falling in this direction. So, if, for instance, the dark matter annihilation depends on velocity, then velocity is itself a function of the phase space distribution. Things are getting non-linear. Well, the very simple solution to that is really that you have a saturation density which scale inversely proportional to the time and to the annihilation cross-section. Okay, so now if I draw, for instance, the number density, log number density as a function of log radius, what it means is that these are profiles for different masses, so it's 10 to the minus 18 in red, 10 to the 6 in blue here. And this is for, well, this is independent on the dark matter mass because it's number density here. And you see that, well, depending on the time at which I consider the saturation density, well, I get different answers. So this is the saturation density I get at recombination time, for instance. So what is above here has been annihilated away, okay? So you end up with a profile which is scored, no? Just due to annihilation processes. So the spike is some part of the spike has been removed by annihilation. All right, so because of this core showing up, there's an interesting scaling also, which results from this. So what I'm showing you is the annihilation rate around black holes, and on purpose I will call that spikes decay. So I can consider the spike as a decaying particle, okay? So a spike is decaying in time, and the decay rate is simply the annihilation rate of particles around, around the black hole. So you see that is standard expression for annihilation of dark matter. Dark matter, you have annihilation cross-section time rho squared, okay? But of course, rho squared is an integral over the volume of the spike, and you see there's a core and there's a remaining spike above the core. So this leads to an interesting scaling relation. So this is log decay rate as a function of log black hole mass. And the colors are for different particle masses. So the red are light particles, so this is 1 MeV, and the blue is very heavy particles, 10 TeV here. So the blue one is this one. So you see that depending on some critical mass, you have different scaling relation. So it's m to the 3 here, and it's linear with black hole mass here. See, and you see that you have a typical transition mass depending on the particle mass. Okay, so
sorry, this is for S wave, right?
this is for S wave, of course. Yeah, yes. For P wave, the calculation is much more complicated because there are non-linearity. So we have not completed the calculation.
That's not done yet.
That's not linear, and I cannot apply this calculation. Okay, so for P wave, there's no. This is work in progress. All right. So what that means is that what you see actually is really the different power laws. So this is 3/2 and this is 9/4. Okay. So this is when you have light particles, you are mostly dominated by the 3/2 component, and this is the scaling you have. And when you turn, when you have very heavy black holes, you turn to the 9/4, okay? And you get this turn in the scaling here. So you see that not only the scaling in black hole mass is different, okay, but also the scaling in particle mass is different. So you see that there's a huge separation due to the mass of particle here, but this is very compact here. So you see, it's not exactly the same relations you have as for classical annihilation. And you see the scaling are very weird. So it's linear in cross-section in this regime, but it's not linear in cross-section in this regime here. So it's cross-section to the 1/3 here. So it's very, very, very peculiar.
Sorry,
yeah.
Even more exotic question than P wave. Have people in this context thought about 3-2 processes for darkness?
Not yet. No. It's only 2-2 here. It's only 2-2. So if any P wave process is considered, this does not apply because it's non-linear and it has to be calculated. So it's not done yet. But for S wave, anything you can imagine in terms of annihilation products can fit into this picture.
Is that also
Yeah.
So if you have such high densities,
yes.
Could you have the back reaction? You know, like how you do dark matter annihilation in the other universe, you have to account for both forward and backward rates.
What do you mean?
Do you have to worry about reaching some equilibrium value rather than just annihilating? So
what do you mean? The annihilation product would somewhat.
If it's optically
it would just escape.
They just escape.
Well, if you assume, well, of course, you would have to consider collisional cross-section.
Right.
So it's the classical picture where you revert the diagram between annihilation and but you could, well, we didn't care about that because well, in principle, the rate should be small anyway, I think. Because the annihilation product is not dense enough in order to
Like self.
yes. So what you can use then is constraints on this kind of scenario. If the other cold dark matter component on top of black holes is WIMPs, of course you have constraints applying to this kind of scenario. So one would be CMB constraints, and the other one would be, for instance, extragalactic diffuse gamma ray constraints. And this is what can be used. And I will show you an example for the diffuse extragalactic ray. So in fact, if you inspect the equation, so this is the gamma ray, the extragalactic gamma ray flux that you have for decaying dark matter. Okay, so decaying dark matter is just, well, the dark matter density times some kind of decay rate, okay, along the line of sight. Okay, and now you can understand why I emphasize the term of decay rate for the spike. So if you write down the equation for the spikes, you get exactly the same. Actually, it's just the fraction, it's just the number density of black holes times the decay rate of the spike. Okay, so you see that you can match actually these two equations, and of course the annihilation final states can be traced back to the decay final states if you have decays to two bodies up to a factor of 2 in mass, of course. Okay, so what we can do is actually to use the existing constraints on decaying dark matter, which are shown here, for instance. So this is lifetime in seconds as a function of dark matter mass for decaying dark matter particles. And this is work done by Ando and Ishiwata using the Fermi data, for instance. And so, well, this is a weird, weird shape for the constraints just due to the fact that for extragalactic diffuse gamma rays, you have contribution from AGNs, things like that. You have astrophysical background that you need to consider in order to extract constraints on dark matter, and this ends up with this kind of weird shape constraints like that. So you see that at each mass, I get a maximal decay rate. Okay, so if I match the two, so the decay rate of dark matter particles to the decay rate of spikes, and the number density of dark matter with the number abundance of black hole, I can turn around and write down a constraints on the fraction of black holes as a function of its mass. Okay, so this is again the plot showing the log of the fraction of dark matter in black holes as a function of log of the mass of black holes. Okay, assuming that the other component is WIMP dark matter. Well, if I assume some kind of canonical cross-section for the annihilation, and if I assume some masses ranging from 10 GeV, for instance, to 5 TeV here, and if I take different values for the kinetic decoupling temperature or time, say, this is what I get. So you see that I get some very strong constraints, which are mostly black hole mass independent here. And you see that the fraction I can constrain, assuming WIMPs exist, of course, and assuming they annihilate this with this cross section. So, of course, this kind of configuration is for WIMP supporters. Well, you end up with constraints which are very, very stringent on the black hole fraction. It's 10 to the -7, which is very stringent. Okay. So, and what is very interesting is that it's almost black hole mass independent. And why does this come? Where does this come? This comes from this ratio here. So you remember that I was showing the decay rate of spike. I emphasize the linear dependency in mass. So if you have a linear dependency in mass, of course, this cancels in the ratio. So it's why you get a flat constraint here, which is not sensitive to the mass of black hole.
Why is there a rogue mass that's like an order of magnitude below the other?
So this is, well, these different, for the different WIMP mass are coming from the fact that if I take, for instance, 10 GeV, I get a constraint which is here. And if I said 200 GeV, I get a constraint which is here. So it's really set by this kind of weird behavior in
Is that the cross section on the y-axis there, thermally averaged or something,
which one?
on the preceding plot?
This lifetime.
This is lifetime.
Oh, in seconds.
So this lifetime is just matching the constraints on decaying dark matter onto the decaying spike. Just matching the two.
And how about translating CMB isotropy constraints on the gang, or those are more stringent?
Yeah, exactly. Well, this is basically the same order of magnitude. So we are, see, this is also work in progress. I have plots that I can show, but this is the ballpark. But well, what is very interesting with CMB constraints is that well, let me just finish that and I will come back to the CMB constraints. Well, I was talking for WIMP believers. And now I can speak for PBH believers, PBH supporters. So you can turn the constraints around and in fact, just believe that there's some fraction of black holes. And then if you believe that there's some fraction of black holes, yes, you can actually constrain the annihilation cross-section as a function of mass, assuming some fraction of black holes and for different masses, for instance. And so again, you see that even though there would be a very, very tiny fraction of black holes, so it's 10 to the minus 7 here, well, you would completely exclude the S-wave annihilation WIMP scenario. That's very powerful. So imagine that tomorrow we detect some kind of subsolar massive and gravitational waves, even though that would be a subdominant component of dark matter, that would already completely ruled out the S-wave annihilation WIMP case. This is very, very interesting in this kind of stuff.
Here, it's all the dark matter, the WIMP.
Yes.
If I assumed
it's 1 minus 10 to the minus 7, the WIMPs.
right. I guess I would be sensitive to the case it's a subdominant relic whose energy density goes like 1 over cross section.
Yes,
So,
yes,
okay,
yes. Any component, in fact, any component which would be able to self-annihilate would be constrained, well, in some fraction at least.
Yeah.
So you can rescale that to any fraction of dark matter you can think about.
The basic point being that it just super enhances the annihilation rate.
Yes,
So
the fact,
Fermi
yeah.
limits are much more powerful.
Yeah,
Very cool.
that's the point. And very, this is very something which is, this is a linear process, so it's very clean. It's very clean. All right, so this drives me to the conclusion. So, yes, this is fully linear, and the key point is that this occurs in a radiation domination epoch, where the dark matter density is very large. Okay, so you really benefit from this large density from the beginning. This is a key point. And the other key point is that well, dark matter is a subtraction of the total density of the universe, such that the mass enclosed in the gravitational influence radius is subdominant in terms of dark matter. So there's no non-linear effect coming from the fact that dark matter could weight as much as the black hole. Okay. Well, the other conclusion, interesting conclusion, is that black holes and S-wave WIMPs are mutually exclusive, and this is, I think, a very powerful statement. And well, this is what I said. If you have subsolar gravitational wave events, that would have strong consequences on dark matter candidates. And also, well, the reverse is the same. If you have hints for annihilating WIMPs, well, that would be also a killer to black holes. Well, what I've shown you relies on simplified analysis in the sense that I've considered monochromatic black holes. So I picked some specific masses. And this also applies only to S-wave. As I told you, P-wave is more complicated because of some non-linear effects to consider. But this can be extended, of course, to P-waves. This is ongoing. To also specific model for black holes, specific mass functions, things like that. And also specific scenarios in which you would have both the black holes and the dark matter in the same model. So you can predict everything, the black hole fraction and the dark matter particle properties from a single model. There are examples in phase transition model, for instance. And what's also interesting is that this provides us with an additional probe of evaporated black holes. So I've discussed, well, maybe if you have a question about CMB, I can discuss that, but you can imagine that black holes have evaporated, are completely evaporated today, but it could be there are still some at the time of CMB, for instance, at the time of recombination. So you could actually probe those black holes also in this in the early universe based on this kind of on this kind of process.
Leave some sort of signature in the CMB.
Yeah,
power spectrum.
exactly. On top of the evaporation itself. And well, and this applies, of course, to any cold dark matter candidate you could think about. I think this is the point. And well, I hope I convince you that well, this kind of mixed scenario is provides us with a rich phenology, and there are still many things to explore. Thank you.
Interesting.
Any questions? I'll ask you more about the non-linear stuff, but
Yeah.
to hold everyone.
Okay.
Well, no question.
Thank you.
We ask you lots of questions.
Yeah. Donc, il n'y a pas de non-linéarité qui vient du fait que la distribution de la matière n'est pas affectée par elle-même. Voilà. Ça, c'est linéaire.
dans la masse.
I'm Matteo, I'm a Yacin's.
Nice.
I wanted to ask you for dinner,
Yeah, you
or,
wanna try?
but if it's only the two of
No,
us and you want to
that's
talk about
coming too.
Macron and, okay,
No,
then I
No,
go.
no, no.
Yeah.
What time are you going?
No chance.
We haven't decided yet, but yeah.
Do I have to sign up